We'll start with a review of what we did on last Thursday, just to remind you of where we are. Thank you. So what we wanted to do is that we have two variables. We have x and y, and we observe y, and we want to estimate x. And so we want to use Bayes' rule to do that. So we have the joint probability that allows us to say that if we could factor out from the joint probability the marginal p of y, then what would be left is the conditional probability, which would then tell us what the x is that we're looking for. And so if our problem is such that our prior is a normal with some mu x and variance sigma xx, so in the case of our nomenclature of estimating, we have some prior x of n given n minus 1, and we have some uncertainty about that prior that looks like this. And then we make an observation, p of y, that has also some mean and some variance. And in the case of our typical equation where y is equal to cx plus epsilon y, this is a normal with a mean that has c and n, c of x, the prior, x of n given n minus 1, and the variance of that equation, which is c times p of n minus 1, c transpose plus r. So that's the distribution of our x, that's the distribution of our y, and the conditional probability of p of x given y is a normal that has some expected value of x given y and some variance of x given y. And what we did on Thursday was to define what these expected values are. So the expected value of x given y is the mean of x plus the variance of xy, variance of yy inverse, times what you observe, y, minus the mean of y, which for the purpose of the system that I defined up here for you, oh my goodness, it's already nonsense. Okay, so for that system, what we have is that the mean of x is going to be my prior plus the variance of xy, which was p of n minus 1 c transpose, then the inverse of the variance of y, which is c p of n minus 1 c transpose plus r inverse times your observation minus the mean of y, which is c times x of n minus 1. And of course, this we recognize as the common gain. And we have the variance of x given y, which is sigma xx minus sigma xy, sigma yy inverse sigma yx. The variance of sigma xx is just a prior. That's the common gain. Sigma yx, the covariance of y with x is c p of n minus 1, which is equal to identity minus the common gain times c times the prior. And we call this the posterior uncertainty. So what I have is a factorization of the joint probability distribution, so that my conditional probability has a mean that is indeed the update of our prior to become the posterior, so we call this the posterior estimate of x. and it has this variance. So when you have a random variable y, and you want to estimate x, in a Bayesian formulation, what you need to do is to basically write the mean and the variance of the joint probability distribution. P of x, y is going to be some normal with mu x, mu y, and the variance covariances of these terms. If you can write this, then you can factor out the conditional probability using this formula that I just wrote for you. And that would be your posterior. Do you have any questions about that? So the Kalman filter, in estimating the posterior, what it's doing you is that it's providing you with the x that has a mean of the posterior distribution, and it has a variance of that posterior distribution. Variance of x given y and the mean of x given y. Okay. So the idea of causal inference is the idea that you're going to have one or more generative models that you're going to try to decide the observation that you're making, is it coming from this model, that model, or some combination of the two. So up until now, we've been saying that there's a particular x and y relationship. But what I'm going to now do is that I'm going to say, well, maybe there's more than one possibility between the relationships of x and y. And in that case, I want to know how should I proceed when I'm not sure what's my generative model. I think it's one of these, two potential models that might have given me my data, and I want to be able to make inference based on that. And to motivate this for you, I want to describe to you an experiment. So suppose that you're in a room, and it has this round structure that you're looking at, and you're asked to fixate here. Means you look here. And while you're looking here, there's a speaker over here. Speaker, like the kind that you buy for your computer. And there's also an LED here. And what happens is that you're asked to press a switch if the light and the sound, you believe, come from the same location. And you're also asked to point to where the sound came from. Now, the trick is that there's going to be a delay between the sound and the LED. So it could occur really close to each other, 200 milliseconds, or it could occur far from each other in time, 800 milliseconds. So temporally, there could be coincidence between them. It's kind of like thunder and lightning. They could occur close to each other, or they could occur far from each other. Position where the speaker is might be close to where the LED is, or it might be far. It might be out here. So in this case, you'd be pretty sure that, yeah, the place that I heard the sound is different from the place that I saw the light. But on the other hand, if I saw the sound, if I heard the sound here and I saw the light here, then I'm more likely to say that I think they came from the same location. So the reason why I describe this to you is because you have a scenario that looks like this. There's a common source, meaning that the two sources of information that you're getting are close to each other. So I'm going to put the X like this. I'm going to say the same thing generates what you hear, the sound, and what you see, the light. Or these are separate things. There's something that gives you the light, something that gives you the sound. Separate things. And so if you believe that there was a common source, the light and the sound, then the place where you heard the sound is going to be influenced by the place that you saw the light. But if you believe these two things are separate from each other, then you're not going to combine the two. So, meaning this, if you have two sensors, say those GPSs, if you believe that they're measuring the same thing, then you should combine the two. But if you believe that they're measuring separate things, well, then you shouldn't combine the two. So is the source of information that the two getting associated with the place you're standing, then you should combine the two. So in principle, you could have a generative model that has two conditions. Let me call it Z is a random variable. If it's equal to 1, I have a single source. What that means is that my Y, Y1, Y2, the two things that I'm measuring, are coming from the same thing. So some C matrix, 1, 0, 1, 0, and here's my X, X1, X2. So it's just measuring X1 plus some noise epsilon. So that's if it's a single source. On the other hand, if Z is 0, then I have two sources. Then what I'm measuring, Y1, Y2, has a different matrix. So if I call this C1 and I call this C2, I have a random variable Z that determines the data that I'm getting. Under some probabilistic scenario, I have a single source. What I'm getting is just one of these X1s. But under some other conditions, just probabilistically, I could be measuring this. And I don't know what is the correct generative model. It's perhaps it's a combination of these two. And so when you ask the person, is it the same location, that you're asking them, what's the probability that Z is equal to 1? When you're asking them, point to where the source of the sound was, you're asking them to estimate X, one of these X's. And so I want to show you how we would do that. So the probability that Z is equal to 1 given Y is, of course, the probability of Y given that Z is equal to 1 times the prior probability that you have a single source divided by all possible conditions, the marginals, which is P of Y given that Z is equal to 1 times the probability that Z is equal to 1 plus P of Y given that Z is equal to 0 times the probability that Z is equal to 0. And so if you think about this, what is it saying? So it's saying that the probability that you had a single source has in its numerator the probability of Y given that Z is equal to 1. So that's this equation here, right? So its mean is going to be C1 times X. And C1 says, well, X1 and X2 have to be the same, which means Y1 and Y2 have to be the same. So if you heard a sound and you saw light, the probability that they came from the single source is that they both have to come from the same location. The more closer they are to each other, the more likely it is that they came from the same location. That's what that numerator says. Probability of Y given that Z equal to 1. So if you heard if you had two inputs, Y1 and Y2, they came from the same source if they are the same, which is what this equation is saying, right? This P of Y given that Z is equal to 1 is a normal with mean C1 times X, right? And C1 times X is saying what should happen is that these two things that you measured should be the same as each other, which is just X1. So the closer they are to each other, the more likely it is that they came from the same source. That's what the numerator says. And of course, the other term here is just your prior. The denominator is saying, well, what's the total sum of the probabilities? It's this plus this. It's just normalizing that ratio. So we can compute this probability of the being a single source by just looking at how similar the two pieces of information they are to each other. If you have two measurements that are measuring the same thing, then the closer they are to each other, the more likely it is that they're measuring the same thing. The farther apart they're from each other, the less likely it is that they're measuring the same thing. That's basically what that's saying. Yeah.
So why is their estimation about the location of the sources?
No. So y is the measurement, right? And so what's this? What's p? P of y given z is equal to 1. That's a normal, right, with mean c1 times x. With variance c1, variance of x, c1 transpose plus variance of epsilon. So the mean of this conditional distribution is just c1 times x, which is what? Which is, you know, if you measure two things, y1 and y2, how close are they to x1?
Right, so but y1 and y2 are just
Measurements.
The physical system. It's
Yeah.
the patient points to.
No, y1 and y2 is what they heard and what they saw. The location of what they heard and what they saw. Yeah, yeah. So if that location is the same, then it's more likely that it had a single source. It's sort of the obvious what you would imagine, right? If you heard the thing and you saw the thing at the same location, it's most likely that it came from the same thing. That's all that's saying. That makes it so that you're more likely to say it had a common source. So, but our intention is not just to say, was it a common source? We also want to say something about where was the place that I heard the sound. So if you believe it's a common source, then what you should do is that when you took two measurements, you should combine the two. If you believe there were separate sources, then you shouldn't combine the two. So our next step is, how do we do that? So my next step is to say, well, what's the expected value of x, given that I measured y and I believe that there was a common source. So what I need to write is p of x and y, given that z is equal to 1, so the joint probability. Because what I want to do is to take the joint probability and from that compute the conditional probability, the posterior that I'm looking for. So that's a normal with a mean mu x, c1 mu x, and it has a variance, let's say p c1 transpose, c1 times p, c1 p, c1 transpose plus r. Suppose this is our joint probability distribution of x and y. So the expected value of x given y and your belief that it had a single source, x is equal to 1, z is equal to 1, is the mean of x plus the common gain, which is p c1 transpose, c1p, c1 transpose plus r minus 1, y minus c1 times mean of x. So that's the expected value. Now, on the other hand, if we have the condition where we don't believe it came from the same source, so p of x and y, given that z is equal to 0, it had a different source. There, in that case, we have a normal with mu x, and now it's c2 times mu x. So our generative model now is the second equation, c2 times mu x, and with the variance of p c2 transpose, c2p, c2p, c2 transpose plus r. So what was c1 and c2 is these equations, this matrix and this matrix. This matrix, if you believe it's a common source, this matrix, if you believe, is two separate sources. So all I've done is just write down the joint probability for that. And now what's my expected value of x given y? So I have expected value of x given y, and it's a common source. I have expected value of, I can write the expected value of x given y, and that it's a separate sources. So here it is, right? Here's the expected value of x and y given that it's a separate source. So the combined expected value of x given y is expected value of x given y z is equal to 1 times the prior probability of z is equal to 1 given y plus the other term that remains, x given y z is equal to 0 times the probability that z is equal to 0 given y. So I had two models that could have generated my data. What I did is that I computed the probability of being the data that I saw coming from a common source. I can also compute the probability of the data coming from separate sources. And then what I do is that I say, okay, what's the location of the sound given that I heard a sound and I saw a light? So what's the expected value of x given y? Well, I have two models. They came from a common source. They came from separate sources. I weigh that by the measurement that I made, the probability of it being a separate source, the probability of it being a common source, and that gives me the expected value of x given y. Yeah.
And how much is normality assumption is accurate? Do we just use this normality assumption to make things easy, or?
Right. So all of the work requires you to have a model, right? And so if the model is saying that the noise is, Gaussian, then this is the solution. But in principle, if it's not Gaussian, then that's okay. But you have to make an assumption about the shape. That's all. Okay, so our problem was this. You have an experiment. You make a measurement. You're unsure whether this measurement that you're making is coming from model A or model B. Which model is generating your data? So you need to figure out the first question, which is that what's the probability of model A given your data? Here we have it. And then once you have the probability of the model given your data, next what you need to know is that what's the expected value of the parameter that you're trying to estimate, x, given that you made your measurement? Well, that x could have been generated by model 1 or model 2. And this is how you divide up the contributions of the two models. And this is where also you would do, a scenario where you want to compare two potential ways by which your data was generated. And you want to know how much more likely is it that the data came from this scenario versus that scenario. This shows you how you can combine it, right? Because this probability gives you an estimate of likelihood that it came from scenario 1 versus scenario 2. So it's causal inference because what you're doing is that you're trying to infer what caused your data. And you have, in this case, two models that you considered. Okay. So I have one other idea that I want to show you today, and it has to do with the influence of priors and how they affect the way we make predictions about events around us. One of the best examples of priors is when you go to pick up something, say a can of soda, and you believe that the can is full, but it's actually empty. So what happens is that you pick it up, you lift it, and your hand goes like this, right? Because you expected it to be heavy, but it was actually light. So you had a prior belief about its estimate, you acted on it, and now if you had to pick it up again, the second time, you'd pick it up with less force. So your hand wouldn't go like that. So people have used this kind of a concept to look at the effect of priors. One of the more interesting examples that I want to show you is the prior associated with physics of falling objects. And the experiment was done on the space shuttle, where the idea was to look to see when an object is falling, when did the astronauts open their hand to catch that object. So the time at which you open your hand is your estimate of when that object is about to hit your hand. So if somebody throws a ball at you, you will open your hand pretty close to the time where you expect to have the thing get there, and then you close your hand. And so you can imagine that now you're an astronaut, you're up in space, you've been there for, let's say, a week, and you can ask the question, well, do they open their hand sometime later? Because they've learned that things in space don't fall at the rate that they fall on Earth. And so I want to set up the problem for us mathematically, because it'll teach us a little bit about how to go from continuous form of differential equations to discrete, which is the way we've been doing things. We've been doing it in the discrete domain, so we can go back and forth between these, and then ask, well, if you had to make an estimate, how do you update your estimate when you have a wrong model of this prior? So a ball falling. Here's our problem. Ball falling with some initial velocity, non-zero. So obviously non-zero initial velocity is important, because when you're in space, if the ball has zero initial velocity, it will maintain zero initial velocity and it won't move. So we're going to give it some push. Okay, so our ball has a state. And that state is its position and its velocity. And we know that if you have been born and raised on planet Earth, then you're going to expect that acceleration is going to be 9.8 meters per second squared, which we call gravity. Okay, so given that this is your expectation, then the dynamical system that we're talking about has the following form. It has change in state, which has velocity and acceleration, being equal to something, which I'm going to write down as a matrix that multiplies our state, x and x dot, plus something else. That's going to be our forcing function. So we want to write the equations of motion of the system. So let's begin with velocity. I'm going to have a 0, and a 1 here. I'm going to have a 0 and a 0 here. I'm going to have a 0 and a g here. So what I wrote is that velocity is equal to velocity plus 0. Acceleration is equal to 0 plus g. Acceleration is not state dependent. It's just a constant. So I just wrote x double dot is equal to g basically with this equation. This is our continuous form representation of dynamics of the system. So if I write this in vector form, x dot is equal to this matrix A, I'm going to put a C on it to illustrate that it's continuous, times state x plus vector B, C. So okay, so how do I write this in discrete domain? What I want to write it is in terms of this, x of t plus delta. Well, that's equal to x at time t plus x dot at time t plus some time delta. So this is some small amount of time that's going to pass. So I want to write my equation of dynamics, instead of in this continuous form, in a discrete form. So let's see if I can do that for you. So that's equal to x of t plus x dot. Here it is. X dot is AC times x of t plus BC times delta. Delta is just some small time, scalar, that we're talking about. So that's equal to identity minus plus B C times delta. And so if you call this
Means the delta.
right, thank you. If you call this the discrete form of the matrix A and BC times delta the discrete form of the vector B, what I have is now x at t plus delta is equal to A times A of D, this matrix, times x of t plus B of D. So that's my dynamics. Maybe I'm going to add some noise to it, epsilon x. All right. So we can write this our usual form, x of t plus delta is equal to A x of t plus B plus epsilon x, and maybe epsilon x is normally distributed, means 0, variance q. And I have make some observation, y of t is equal to c x of t plus epsilon y, and epsilon y is normally distributed with variance r. And c is identity, so we can observe position and velocity. So we start with some prior. We have a normal distribution of x of t given t minus delta with variance p of t given t minus delta. And we make an observation. We look at the ball and we see it at some location, and then we make a posterior prediction where it's going to go. So we say x of t given t is x of t given t minus delta plus our common gain times what we observed minus where we thought it would go, x of t given t minus delta. And our common gain is our uncertainty times the inverse of the measurement noise. Once we have our prior on this trial, we have our posterior on this trial after we make an observation, then we have prior on the next trial, which is x of t plus delta given t. That's just equal to x of t plus delta given. Let me fix this. And my posterior on my prior uncertainty on the next trial is a p of t given t a transpose plus q. Okay, so that's fine. That's the math. What does it mean in terms of our ball? So in space, our ball is going to fall as follows. So if this is time, and if this is ball height, with constant velocity, it's going to fall like this. But if it was on Earth, it would fall with acceleration, it would fall like this. So this is with 1g, this is with 0g. So at any given time, t, we make a prior belief that it's going to be here, x of t, given t minus delta. We make an observation here, y of t. It hasn't fallen as far as we think. We make a correction. This is x of t given t. We move toward our observation. Then we make a prediction forward in time. So this is what we had as our posterior. We believe that it's going to fall the same way as with gravity, right? So it's going to fall here at our next time point. This is x of t plus delta given t. We make an observation. Here's our observation. That's y of t plus delta. And again, we make a correction. So as this ball falls, like this, is our prediction, is this is how it actually is going to fall. Every instant in time, as we make a prediction, we make a correction. Like this. Because our equation of motion here has a prior that says it's going to move with gravity. This equation here. So we're going to assume that the next thing that we're going to see is going to be pushed by gravity, which is this vector b. But in reality, b is 0. It's in fact moving along a straight line. And so we make a prediction it's going to be falling farther down. Every instant in time, our brain is going to actually make a measurement. It's going to say, whoa, it's here. It's not here where you thought it was, so you make a correction. So let me describe it this way. You have a dynamical system that you have a model for. You believe this dynamical system is affected by gravity. But that doesn't mean that you're going to be, making an estimation continuously that's going to be dependent on only gravity. You also make observations, so you see where the ball is. And every time you see where the ball is, you correct based on what you see. You influence your prior, you bring it closer to what you observed. And then you make another prediction in the future. Your prior makes it so that, your model is always tracking the reality, but it's not perfectly compensating for it. Why? Because this equation, which is your prior, it says your next state is going to depend on the previous state plus this term b, which was gravity. This gravity doesn't exist in reality, so your model is wrong. But what happens is that when you make an observation, here it is, you make an observation, you correct what you predicted. And so you get closer to reality. So your posterior becomes closer to what you observed. And then you do it again. Until at some point, somehow you learn that this model is wrong, this B is wrong. And this may take a very long time. So when they did this experiment on the astronauts, as long as they were in space, they had the wrong model. Perhaps it takes months and years, who knows, for them to learn the correct model of physics. So the prior is wrong, based on a wrong model. It pushes you away from your observation, but the fact that you make measurements, it brings you closer. And then you continuously do that. Yeah.
So to update your model, you're saying these experiments took like a time course of months?
No, they only did it in the time course of a week.
Okay.
And in the week, what they saw was that people just opened their hand as if they were standing on Earth. Their expectation of when the ball would hit their hand was not calibrated yet.
So they weren't properly updating that.
Yeah, yeah. So their B in this dynamical system was consistent with one you would have if you hadn't been in space. But your errors are much smaller than a system where has this, has no feedback from the environment. So they can see the ball as the ball is falling. And so they improve as compared to, something that just says the ball is falling, open your hand when. So if you only have one chance to open your hand, you never sample the system, then you're going to be way wrong. But if you can see it, then you can update, and your hand will open more closer to when, the ball actually does hit your hand. So I just want to make sure we understand what I'm saying here. So if you had no feedback from the environment, then here's when you would open your hand. But if you do have feedback from the environment, then you're going to open your hand here, much closer than when the ball comes. Why? Because every instant in time, you get feedback where the ball is. Your model is wrong. It's making predictions on the next time point that's farther away than it actually the ball falls.
But isn't that time course much slower than like in your lab if you're doing that
Yeah.
robotic experiment? So what's different?
So the visual feedback that you get is on the order of 200 milliseconds. That's the time point that you're going to... So if the task is longer than 200 milliseconds, which in this case would be, because the ball falls presumably fairly slowly, say a couple of seconds, you're going to have many instances of time to update your model. Get closer to reality. Yeah.
Can you clarify a little bit, how would you kind of separate whether the improvement is due to updating the model or based off the feedback, I guess?
So they're one and the same. So in this case, when I say, well, maybe I misunderstood what you said. When you say update the model, you mean update B?
Yeah.
Okay. The only way to do that is to have a scenario where you don't allow for feedback. If you don't allow for feedback and you say, when do they expect the ball to be there? If all they have, or you make the feedback really noisy, so then they have to rely on their internal estimate. That's how you can tell.
So that's within the course of a single trial, not between different trials.
Correct, yeah, within the course of a single trial. Yeah. Essentially, you have to remove the ability to update. Compare their prediction with the data that they're actually sampling.
If for example after 1 week trial,
Yeah.
then if we, I think the case is that then after 1 week we will lose our trust to the buyer and we will be more believe that.
That's a great question. So that maybe the common gain will change. So maybe B won't change, but the gain, which is how much you learn from error, will change. Yeah, maybe the uncertainty that you have will be high, and therefore you will believe what you see more.
Then if after 1 week we just omit the vision, do they just return to the plane?
Right.
Or
So
do they
so that's the way to tell the difference between a change in the common gain versus change in the structure of the model that you have, right? And so these are all important questions about how do you know the behavior of the individual that you're seeing, how did they do that, what they did. And so those are the experiments that you would design. Okay, good questions. Short lecture today, so go out, enjoy the nice weather, and I will see you Thursday.